Year 12, today we're going to start a new topic on exponential and logarithmic functions, and specifically we'll be looking at exponential functions today with a base of e. So our learning intention is we're going to evaluate, manipulate and graph exponential functions with a base of e. Now you might ask why we're looking at exponentials specifically with a base of e. Well, they have some fairly unique characteristics. And if you have a look at the graph here of y equals e to the x, e is also known as Euler's number, and it has a constant value 2.718 to 3 decimal places, but you can see that this is a non-recurring decimal. And what's special about this value of e? Well, let's have a look. So if we have a look at this point where this function crosses over the y-axis, and that's when x equals 0 and y equals 1, if we're going to look at the slope of this tangent that meets the curve right there, the gradient of this is, it has a gradient of 1. Now that's fairly significant, that when x equals 0, this has a slope of 1. When x equals 1, so out here, when x equals 1, if we looked at the slope of this tangent when x equals 1, it has a gradient of e. So if we substitute when x equals 1 into our function, we'll notice that it has a gradient of e. So that actually tells us a little bit about the derivative. If we've got a function in the form y equals e to the x, and our derivative then is also e to the x. And when we look at it in terms of the integral or the area under the curve, we notice something also particularly interesting. The area under this curve in here is actually e to the x as well. So the integral of e to the x with respect to x is actually e to the x plus c. So it's because of these particular properties that an exponential with a base of e is really important for us to analyse and focus on in this topic. So let's have a look at what we've discussed so far. We know that the value of e is this constant value, approximately 2.718. We know that the derivative of e to the x is also e to the x. We know also that the gradient at the y-intercept to the curve is 1. And we can see that the domain is all real numbers because we can substitute in any value for x into our function, and there are no restrictions on the value of x that we can substitute in to our original function. And we can see when we look at the graph that the range is y is greater than 0, because if we look at the graph of y equals e to the x, it's all above the x-axis. So in other words, it's all, the range is when y is greater than 0. And we can see that we've got this horizontal asymptote here because our function y equals e to the x is approaching the x-axis, but it never actually touches. So y equals 0 is our horizontal asymptote. We can see that this function is 1-to-1 for every x value. There's only one corresponding y value. So its inverse relation is also a function. If we were to differentiate the function again and find the second derivative, so we take e to the x and we differentiate that again, we actually end up with the same result again, which is e to the x. And we can see when we look at this curve here, on this curve, the function's always concave up. So if it's concave up, that tells us about the second derivative, and the second derivative is greater than 0, and it's an increasing function. So in other words, when we look at the derivative here, y dash is greater than 0 for all values of x. Next, we're going to have a look at how to evaluate the answer to an exponential with a base of e. So if we're looking at this function here where we've got a equals e to the power of -4, what that actually means is we've got 1 over e to the power of 4. 4, because our coefficient here is 1 in front of e, which becomes our numerator. And then if we use our calculators, when you put it into the calculator, press 1 divided by or 1 over, and then you'll need to press shift and then the natural logarithm button, which looks like an ln, and above that ln you'll notice on the left hand side there's an e to the power of. So you put in 1 divided by e to the power of 4, and your answer to that, to 4 significant figures, is 0.01832, because we need 4 significant figures. So here are our 4 significant figures. For part B, to find the square root of e, you'll need to put in your calculator the square root button, and then shift and then the natural log button to bring e onto the screen, and then you'll need to put in e to the power of 1, because we know that the power here is 1, and the answer to that is to 4 significant figures, 1.64, and then this will be our 3rd significant figure, the number 4, and the number after that is 87, so that's going to be closest to 9. So 1.649 to 4 significant figures. Okay, to expand and simplify, we use the FOIL method that we've used previously, where we multiply first and then last and then inside and then outside. So then we have e to the power of 4x times e to the power of 2x plus e to the power of 4x times the 3 plus then 3 times e to the power of 2x plus 3 times 3, which is 9. Now let's tidy this solution up a little bit. When the bases are the same, you maintain the same base and you add the indices together. So now we're looking at 4x plus 2x becomes to the power of 6x plus 3 times, let's put the 3 in front, e to the power of 4x plus another 3 times e to the power of 2x plus 9. Now, when we look at these terms here, you'll notice that the indices are not identical, so therefore we can't simplify them any further than they are currently, and we'll leave it in that form. Okay, with this next question, I'm going to write it out slightly differently so you can see what the common factor could be, because ultimately we want to factorize the top, take out the highest common factor on the top and the highest common factor on the bottom, and see if we can simplify it a little bit. So we've got this e to the power of 2x. Now, can you see that e to the power of 3x is actually e to the power of 2x times e to the power of x? Because remember, when we multiply and our bases are the same, we add the indices. So here we've got a 2x plus an x add together to give us this 3x here. Over e to the power of 4x could be written as e to the power of 2x times e to the power of 2x. Again, bases are the same and our indices could be added together to give us 4x. Now, can you see that we've got an e to the power of 2x on the bottom and on the top? So let's take out this e to the power of 2x. And then what are we multiplying this first term by to get e to the power of 2x? 1 minus, if we take out this e to the power of 2x in our second term up the top, we've got an e to the power of x all over e to the power of 2x times e to the power of 2x. Now we've taken out this common factor of e to the power of 2x, so we can divide through the top and the bottom by that e to the power of 2x, and we end up with now 1 minus e to the power of x over e to the power of 2x, which is simplified as much as possible. Now these transformations on this slide should look familiar to you. We spent time at the beginning of our first unit for the HSC course looking at how to shift horizontally, vertically, reflect in the x-axis, reflect in the y-axis, and rotate a function about the origin. So just take a moment to look through those. At this point, I want you to focus on the 3 with the red asterisk and just remind yourselves that if you want to shift a graph horizontally to the right, you replace x with x minus h. If you want to shift a function up, you replace y with y minus k, and then you end up with a function in this form where you've got the function plus a constant k at the end of that function. If you want to reflect in the y-axis, you replace x with a negative x. So you end up with a function in the form of y equals f of negative x. So we're going to focus on these particular transformations in the next question. Okay, so let's have a look at each of these 3 transformations. You'll notice in part A, we've replaced x with negative x. So we said previously, what that will do is reflect this original function here that we've got drawn, y equals e to the x, reflecting that over the y-axis will give us a function that looks something like this. Have a look at part B. Now let's think about this. If we're going to add a constant onto the end of our function, that's essentially replacing y with y minus k. And in that particular case, that will shift our function up 3 units. And then in part C, so instead of having this y-intercept here for part B, at 1, it's going to move up 3 units and pass through the y-axis at y equals 4. And finally, in part C, replacing x with an x minus 2. Remember from our previous slide that this will shift our function 2 units to the right. So you imagine this function here moving 2 units in that direction. So let's look at the next slide, what our final functions look like. Now remember in part A, we replaced e to the x, we replaced our x with a negative x, and replacing x with a negative x reflects it in the y-axis, and you can see here this is a reflection of our original function. If we're going to sketch e to the x plus 3, adding this constant of 3 onto the end of our function will essentially move our function y equals e to the x up 3 units. So previously we had an asymptote along here, along the x-axis, or in other words, where y is equal to 0. Now our new asymptote is up here at y equals 3. Our original y-intercept was previously at 1. That's been shifted up, and that's now at 4 units. And finally, in part C, remember replacing, if we want to find this function here, e to the x minus 2, we've replaced our x with x minus 2. And what that will do is shift our function 2 units to the right. And that's essentially what's happened here. Next, let's recall some of the work we've done previously on dilations. And you'll remember that if we're going to dilate a function and the dilation factor is between 0 and 1, then that graph is going to get compressed. It becomes smaller. Now, if that dilation is a factor of -1, that's actually a reflection across the y-axis, which is what we did previously in part A. Now, you remember I spoke to you earlier about the reason we're focusing on exponential functions that have a base of e is they have this unique property whereby the derivative of e to the x is still e to the x. In our final example today, I want to revisit some work we did in Year 11 on tangents and normals, where we'll have a look at the tangent to the curve. And specifically, at the curve y equals 2e to the x. So when we know to find the tangent or a normal to a curve, we need to differentiate. And our derivative of e to the x is just e to the x. So the derivative of 2e to the x will simply be 2 times our derivative of e to the x. And if we want to find the equation of the tangent at point A, and at point A, we know x equals 1. So where x equals 1, we're going to find our gradient of the tangent. So we're going to substitute x equals 1 into our derivative. So we end up with 2e to the power of 1, which is simply 2e. So this is our gradient of our tangent. Now, if we know when x equals 1, we also need to find what the y value was. So when x equals 1, then y is going to equal, we substitute x equals 1 into our original function, which becomes 2e to the power of 1, which is also 2e. So now we have a point with a coordinate x equals 1 and y equals 2e. And that's the coordinate that we're talking about here, which is point A. Okay, and we know that the gradient of the tangent at point A is also 2e because we found that previously. So let's substitute into our point gradient formula, which is y minus y1 equals m outside of x minus x1. And substituting in our y value of 2e, we end up with then our gradient, which is m times x minus 1. Let's expand and simplify. We end up with y minus 2e equals 2e times x minus 2e. Now we've got this minus 2e on both sides of our equations. If we add 2e to both sides, it's going to cancel, and we end up with then y equals 2e times x is our equation of the tangent. Now to find the equation of our normal, remember that the gradient of the tangent times the gradient of the normal equals -1, and one is the reciprocal of the other. So the gradient of our normal is going to be the reciprocal of the gradient of the tangent, which was 2e. So we end up with gradient of a normal is 1 over 2e. And now to find the equation of this normal, we're going to substitute that into our point gradient formula. Y minus y1, which again is 2e, equals -1 on 2e times x minus our x1, which is 1. Let's take this -2e that's on the denominator over here and multiply that to the other side of our equation. So we end up with 2e times y minus 2e times 2e becomes 4e squared equals -1 times x minus 1. Let's move to the solution on the next slide so we can finish off this example. So on the previous slide, we got to this point here where we were multiplying both sides by 2e, and we ended up with 2ey minus 4e squared is equal to -1 outside of x minus 1, which we can multiply everything inside the brackets by -1 and end up with -x plus 1. Tidying all of this up a little bit, we've brought the x over to the left-hand side. So we end up with x plus 2ey equals, and take that constant of 4e squared to the other side, and we end up with this final result here. Now in part B, we're asked to show that this tangent here goes through the origin, and we can see if we have a look at this equation, it's just in the form of y equals mx plus 0. There is no constant. So when x equals 0 here, if we were to substitute x equals 0 into y equals 2 times e times x, which is 0, we're going to end up with y is also equal to 0. So therefore, it passes through the origin. In this second equation, we were asked to, this normal that we have here, we were asked to find where it's going to meet the x-axis. Well, all the way along the x-axis, our x-intercept is where y is equal to 0. So if we substitute y equals 0 back into this equation, we end up with x plus 0 is equal to 4e squared plus 1. So in other words, x equals 4e squared plus 1. So this is where our normal is going to intercept through the x-axis. So in other words, the coordinates of B are going to be, this is our x value, 4e squared plus 1, and our y value is going to be 0. And you'll see a solution to this question on the next slide. And finally, we've been asked to find the area of this triangle AOB. Okay, now we know that the coordinates of A are when x is equal to 1, and we found that earlier, that had the coordinates 1 and 2e. And we know this length here, OB, must be the same as this x value here, which is 4e squared plus 1. So our base of the triangle has this many units, and the height of this triangle here is 2e. So we're simply going to substitute our base as 4e squared plus 1 and multiply it by our height, which is 2e, and halve that. Substituting it into the formula, half the base times the height, we end up with this result here. Now finally, I'd like you to have a go at exercise 5A, please. And I'll be online in the live stream document to be able to answer questions.